let's talk about some additional limit techniques. Now, we've learned the basic limit laws. We've learned how to separate different terms using sums or differences or constant multiples, various laws that way. And we've also learned about limits of polynomials and rational functions. But there is a case that we haven't talked about yet that can be a bit of a headache. If we're looking at a rational function, and the value that we're trying to approach causes that rational function to be 0 on the numerator and the denominator, we're in big trouble. So let's take a look at what's happening here. I've got the limit of a function. The function is x squared minus 1 over x minus 1. And if I try to do direct substitution where x is approaching 1, I would have 1 squared minus 1 on top, and I'd have 1 minus 1 on bottom. That would look like 0 divided by 0, and that is not good. That should make you want to cry. So this is what we call an indeterminate form, 0 over 0. And you should always check to see if you have an indeterminate form. If you don't, then you can go ahead and use direct substitution. But if you notice that you have indeterminate form and you're trying to evaluate this limit, I recommend making a note that you have indeterminate form and then thinking about how to get around that. Now, something super important. I see this mistake every semester. You find that you have indeterminate form, and so you write it's equal to 0, but that's incorrect. This is not equal to 0. In fact, we're not sure what it's equal to. That's why we call it indeterminate. When we have a function whose limit gives us an indeterminate form, what we'll do is find an identical function that we can use instead to evaluate the limit. I've got two graphs on the screen. One is the graph of the function f. That's the one that we were trying to compute the limit for. The other is the function g. Now they look identical except for at x equals 1. Notice that for f at x equals 1, I have an open circle, meaning my function is not defined there. However, g is defined there. So this technique says if you have an indeterminate form, what you ought to do is look for a function that's identical everywhere except for the point that's producing the problem. And if we think about it, this function f is very much like this function g if we simplify. The numerator of the function f is a factored pattern, a difference of squares. So if we remember a term squared minus another term squared, that's a difference of squares, and that can be written as the product of two things, factored. It becomes a plus b, a minus b. So if I'm looking at x squared minus 1, let's pretend like that 1 was squared because it helps us out to do it. X squared minus 1 would become x plus 1, x minus 1. That's my numerator. My denominator has x minus 1 in it. So I can divide off that common factor, leaving behind x plus 1, which is exactly what we have picked g of x to be. So this idea says if you are evaluating a limit and you get indeterminate form, we're going to use some algebra to manipulate our function into another function. So we're going to change it into something else, something that won't give us a problem at the value that our limit is approaching. We have the problem-solving strategy on the screen here so that we can follow our guide. So this strategy is specifically for calculating limits of rational functions. So we have a polynomial on top of a polynomial. And this rational function that we're working with does in fact have an indeterminate form. So the first step in our problem-solving strategy, make sure that we actually do have the indeterminate form. If we can use direct substitution or our regular limit laws, we probably ought to do that. So first we're going to check. Let's go ahead and look at the function in the limit that we're trying to evaluate here. X is approaching 3, so we're going to try direct substitution and see if it gives us a problem. And sure enough, trying direct substitution with x approaching 3, we do get an indeterminate form, so we know that we are not able to use the old rules that we had. Next we move on to step 2. Step 2 says let's find a function that is very similar to the function that we're starting with, except it doesn't give us the problem at the value that our limit is headed to. So to find our function, we have 3 tips. Tip A, tip B, tip C. The first one says that if f and g are polynomials, meaning we have a rational function, our numerator is a polynomial, our denominator is a polynomial, if that's the case, we should factor each function and cancel out any common factors. So looking at our function, we certainly do have a polynomial on top and a polynomial on bottom, so let's factor them completely and see what we can simplify. In the denominator, I have a trinomial, and maybe it's been a while since we factored trinomials, but I'll show you how I like to factor them. So I have 2x squared minus 5x minus 3. I take the coefficient on my x squared term and my constant term, and I multiply them together. So I multiply 2 times negative 3, which is negative 6. Then I list out all the factors that I can have for negative 6. So I could have 1 times 6, where one of those numbers has to be positive, one of them has to be negative, or I could have 2 times 3. Again, one of those has to be positive, one of them has to be negative. I'm going to pick the pair of numbers that when I add them together, I get my middle number, negative 5. So if I made 1 and 6 with a 6 negative and the 1 positive, when I multiply them together, I get negative 6. When I add them together, I get negative 5, so that is the winning choice. I'm going to use positive 1 and negative 6 to separate my middle term. So I'm basically going to replace the negative 5x with a negative 1x, sorry, not a negative 1x, with a positive 1x and a negative 6x, because those things are equivalent. So I'll rewrite my trinomial with an x minus 6x in the middle instead of the 5x. And then I have 4 terms, which allows me to group 2 pairs. I'm going to find the greatest common factor in each group. So in my first group, the greatest common factor is x, leaving behind 2x plus 1. In my second group, I have 2 negatives, so I'm going to factor out a negative. I also have a factor of 3 in each term, so I'm going to factor out a negative 3, leaving behind 2x plus 1. And then I notice that the 2 terms that are left have a common factor of 2x plus 1, so I'll factor that off. From the first term, I have an x left behind. From the second term, I have a minus 3. And so that's the factored form of my denominator. Having it written like this, I'm able to see that there's a common factor in the numerator and the denominator. The x minus 3 will divide off, leaving behind x divided by 2x plus 1. This is the function that is nearly identical to our original function, but should not give us the problem at x equals 3. So we will compute the limit for this function and say that it's going to be equal to the one we started with. Now this guy, I'm allowed to do direct substitution, so I'm just going to replace my x's with 3's and simplify. That limit comes out to be 3 over 7. Now, there are 3 tips for step 2, so we're going to try an example that covers each one of those tips. So let's start with a new function here. This function is not a polynomial in the numerator, not a polynomial, well, it is a polynomial in the denominator though. So first, we will check to make sure that we can't just use direct substitution. So let's go ahead and try it. Let's see what happens if we replace x with -1. And sure enough, we do arrive at an indeterminate form, which means we need to use some clever algebra to get us out of this mess. Moving on to step 2, we want to find that twin function that looks just like our function but doesn't have the problems at -1. So we're going to read through our tips. We know that we are not going to use a because we don't have a polynomial in our numerator. That radical means not a polynomial, so we can't use that first one. Let's move on to b. If the numerator or denominator contains a difference involving a square root, well, ding, 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 that's exactly what we have in the numerator. We have a difference, and one of the terms that's in the difference has a square root, so we definitely want to use tip B. The tip is we should try multiplying the numerator and denominator by the conjugate of the expression involving the square root. All right, maybe we have forgotten what a conjugate is. A conjugate is when you keep the exact same terms, but you change the operation. If it was addition, change it to subtraction. If it was subtraction, change it to addition. So the terms that we're going to conjugate are the ones that involve the radical and the difference. So for us, we're going to use the conjugate, and I'll write it down here. So our conjugate is the radical x plus 2 plus 1. So notice that in the original problem, we have minus. In my conjugate, we have a plus. So we just swapped the sign. That's how we make the conjugate. This tip says to multiply the numerator and the denominator by this conjugate. So let's go ahead and do that. And when we write it out, we should be very careful to make sure that we know the entire numerator is multiplied by the entire conjugate, as well as the entire denominator is multiplied by the entire conjugate. Parentheses is the best way to illustrate that. Now we're going to use that FOIL technique to multiply out the binomials in the numerator. We are not going to multiply out the denominator. Let's leave that factored. Multiplying out my numerator, I have the square root of x plus 2 times the square root of x plus 2. In other words, I have the square root of x plus 2 squared. Next, I have that square root of x plus 2 times 1. Then I do -1 times the square root of x plus 2. And then lastly, -1 times +1. And when we simplify this, we're going to notice that things clean up very nicely. The two middle terms in my numerator, root x plus 2 and minus root x plus 2, they wipe each other out, they're gone. The radical on my first term reduces with the square, so that actually just becomes x plus 2, so let's copy that down. And then we have the -1 in the numerator, and we'll copy our denominator down. And we'll copy our limit symbol. In my numerator, I have x plus 2 and then -1. Let's go ahead and add those two constants together. So instead of x plus 2 minus 1, it would just be x plus 1. And look at how wonderful this is. That x plus 1 in the numerator matches with the x plus 1 in the denominator. We can divide them off, leaving behind a factor of 1 in the numerator. So finally we have 1 over the square root of x plus 2 plus 1, and now we're ready to evaluate our limit as x approaches -1. Now that we've eliminated the indeterminate form, we can use direct substitution. So we'll replace x with -1. We have 1 over the square root of 1 plus 1, which comes out to be 2. So our final answer for that original limit is 1/2. So anytime you're calculating a limit that has an indeterminate form and you see a radical that's involved in a sum or a difference, you'll use this conjugate technique to find that twin function that you can evaluate the limit using direct substitution. We've already seen how to use tip A and tip B, so spoiler alert, this example is for the third tip that we have. This applies, of course, if we have an indeterminate form, so we first need to check that. Step 1, make sure that you're not using a hammer when you could use a finer tool. So we'll check and see if we replace x with 1, do we get indeterminate form? So if I turn that into a 1 and that into a 1, I have 1/2 minus 1/2 on top, which gives me a 0, and 1 minus 1 on bottom, which gives me a 0. So we're definitely dealing with an indeterminate form here, so we will use this tip to try and help. The tip is, if you're dealing with a complex fraction, well, we absolutely are dealing with a complex fraction within a fraction. I have a fraction in my numerator, and we have 2 actually. So we have fractions within fractions. This should help us. The suggestion is simplify it. So we need to simplify our complex fraction. To do that, we need to find the LCD of all the terms in the expression. Within this expression, I have a denominator from the first term, which is x plus 1. We have a denominator from the second term, which is a 2. And in our denominator, we could say that we have denominators of 1 for each of these terms, but that doesn't really bring anything to the LCD, so we'll leave those out of it. Our LCD needs to contain both of these factors. So we have x plus 1 times 2. That's our LCD. I'm going to multiply that to both the numerator and the denominator. Multiplying our LCD like this is going to help us simplify whatever has the extra fractions. So looking at our numerator, when I multiply the LCD to our first term, we have 1 over x plus 1 times 2 times x plus 1. The x plus 1 factors are going to reduce, leaving behind only a 2. When I multiply the LCD to that second factor in the numerator, I have negative 1/2 times 2 times x plus 1. This time it's the 2's that reduce off, leaving behind a minus times x plus 1. So hitting that numerator with our LCD quickly simplified it. We could have gotten a common denominator between the two of them and then divided out everything, but this is really the most sophisticated way of simplifying our complex fractions. The denominator doesn't have any fractions within it, so we're going to leave it completely factored, but I will change the order that the factors are written so that it's 2 times x minus 1 times x plus 1. Now we need to simplify our numerator. We are subtracting a group of terms because of the parentheses, so let's make sure we distribute that negative and then copy down our denominator. We haven't changed anything down there. And then we can simplify the terms in the numerator, adding together the 2 and the negative 1. And now we're at a spot where it's easy to get your head kind of spinny. The numerator has 1 minus x. I don't have that same thing in the denominator, but I have something awfully close. So what we need to do is multiply by a double negative so that we can flip the signs in our numerator to make it match with the denominator. So I'm going to multiply my entire numerator by 2 negatives. The reason why that's okay is because a negative 1 times a negative 1 is a positive 1, so it's almost like it never happened. I'll take one of those 2 negatives and multiply it into my 2 terms. So that would look like negative 1 plus x is being multiplied by a negative 1. And then I'll keep the bottom how it is. Now this is much closer to matching the term negative 1 plus x and my denominator x minus 1. I just need to reverse the order that these are written in. And now we can divide off that common factor, leaving behind negative 1 over 2 times x plus 1. All of that is what we're calling simplify it. So there was a lot of algebra there, and if we're being completely honest, algebra is the thing that's the hardest in calculus. So once we have our complex fractions simplified down to this much nicer version, we can apply our limit using direct substitution. Now, just to remind you how much of this is calculus, that's the calculus part. All of the rest, that's algebra. So if you say calculus is hard, do we really mean the algebra part is hard? Yeah, probably.